It's the Adam Ragusia podcast, episode 53. Hey, what sound does a tomato plant make when it's thirsty? That's not a joke or a Zen koan. There is an actual sound that tomato plants make when they're thirsty. A whimper or scream, if you will. An audible indication of physiological stress. And I'm going to play it for you right now. You hear it? Here it comes again. All right, I'll play it 3 times in a row, just so you don't miss it. Just sounds like a click. It goes by so fast, right? And consider this, I slowed it down. The actual sound is ultrasonic, meaning it goes by far faster and is therefore far higher than any sound humans can hear. To make this tomato scream audible, I had to stretch it out to 8 times its original duration. Therefore, what you're hearing is 8 octaves lower than the real thing. Here it is again, the sound of a thirsty tomato, and I'll play it 3 times. Believe it or not, there really may be something kind of like a botanical vocalization going on there. It's a sound that a plant seems to have evolved to make when it is thirsty. And we're not talking about the sound that like any desiccated plant makes when its leaves go dry and they rattle around in the wind. This click, this is the sound made by a living green tomato plant that just hasn't had water for a few days. In fact, the plants seem to make the most ultrasonic clicks per day around 5 days after their last watering. And then the sounds that they make taper off as the plant gets in worse and worse shape. And it's not just tomatoes. This team of researchers at Tel Aviv University, whose new paper I have linked in the description, it is free. This team has also put microphones around wheat plants and corn plants and grapes and tobacco and other plants, and it's not just tomatoes that click when thirsty. And they don't just click when thirsty. The plants also click after having been injured, cut. They also click when infected with damaging viruses. The sound of the clicks they make is different depending upon which of those stresses they are enduring. Thirsty tomatoes click differently than injured tomatoes. Those scientists in Israel mainly focus on tomato plants in their big new paper. Tomato and tobacco, which is of course a close botanical relative of tomatoes. They are both nightshades. Tomato is my favorite edible plant. And I'm a failed composer who works in media production and loves science fun facts. So of course, I'm going to talk about this screaming tomato study for an entire episode that is going to verge from botanical to acoustical areas of content. I love tomatoes, and the notion of a tomato screaming in discomfort is dismaying to me. Luckily, that's probably not the best way of thinking about what's happening here. That is a highly anthropomorphic interpretation of what's going on. No one knows exactly what's up with these little clicking sounds, but those scientists have raised the possibility that it may be some kind of plant communication. A communication may sound like too strong a word because it kind of implies intent, and no one is arguing that plants have nervous systems, let alone anything like a brain that could generate thoughts. But if you figure a computer is also an inanimate object, do computers communicate with each other? On one level, yeah, obviously, duh, they do, but you could also say that computers don't communicate with each other. People communicate with each other via computers that people program. Sure, fair enough. But evolution is kind of like programming. Evolution endows living things with a set of instructions to execute. The instructions are simply encoded in genes instead of in Python. And I mean Python, the programming language, obviously. I probably shouldn't have picked the one programming language that's named after a living thing for that example. But anyway, genes are codes. They simply encode information by alternating 4 different amino acids in different orders and combinations, as opposed to alternating zeros and ones in different combinations. And now is when some pedant starts drafting an email about how Python is actually a high-level language, meaning it's written in normal letters and numbers that humans can understand. It has to go through a compiler to convert into machine code, which is the binary code that's actually processed by the computer. And thanks, dude, I know that Python isn't just ones and zeros. It isn't ones and zeros at all. And I know another difference between plants and computers is that computers are programmed by people who have thoughts and feelings and goals and such, and plants are programmed by the forces of evolution, which has no thoughts or feelings. Evolution is merely a succession of mistakes, random mutations, and if a plant's genes happen to mutate in such a way that benefits the plant or its offspring, then the plant spreads this mutation around and it sticks. Why might plants have evolved the ability to effectively scream in pain? Well, let's talk about what these Israeli scientists actually observed, which of course is not literally a scream of pain. That's just the most convenient way we have to describe it, because we developed our language chiefly for the purposes of expressing things about ourselves, and we're people. Describing plants with a language designed to describe people is like using machine code to say how you feel. It's possible, but awkward. This is why even brilliant biologists who need no lecture on the non-teleological nature of evolution will say things like, this plant is much happier in X conditions, or this plant really wants to do X, or it hates Y. Plants don't have feelings, and we don't need an internet pedant to send us a DM to that effect. Anthropomorphism is just a much more convenient way to talk about plants in a human-oriented language like English. These particular humans in Tel Aviv put tomato and tobacco plants inside acoustically isolated boxes. Then they put 2 microphones on each plant, recording at 500 kilohertz. That's 500,000 samples per second. In contrast, the sound of my voice right now is being recorded at 44,100 samples per second, which is a pretty standard sample rate for digital audio because it's a little more than twice the rate of the highest frequency sound that any human can possibly hear. The highest sound that any person can hear is about 20,000 hertz. Hertz is a measurement of cycles per second. A cycle of a sound is the positive phase of the wave followed by the negative phase. So vibrating objects alternatingly push and pull air against your eardrum as they vibrate back and forth. That's the peak and the trough of the wave. A complete cycle from equilibrium air pressure to maximum pressure, down to the maximum negative pressure, aka pull or vacuum, then back up to equilibrium again. That is the cycle measured in hertz. Though, confusingly, people also use the word hertz to describe the recurrence of any event per second. Like anything per second is often expressed in hertz, even if it's not a 2-part cycle, like a sound wave is. Even if it's just a single thing, like a sample, people still will call that hertz, and it's confusing. A digital sample is just one thing. It's just a number to indicate how hard the air is pushing or pulling at the particular instant at which you sample the sound. The particular instant at which the sample is taken. To represent a sound with a sequence of discrete numerical samples, you have to sample at twice the rate of the fastest or highest sound that you want to record, because you need to capture information about the peak and the trough of the wave. You have to get at least 2 samples per acoustical cycle. And then, as this thing called the Nyquist-Shannon theorem tells us, you actually have to sample a little more than twice as fast as the fastest frequency you're trying to record. Imagine if you were recording a 20,000 hertz sound with 40,000 samples per second. If sample number 1 happens to fall at exactly the beginning of this 20,000 hertz sound cycle, you will record silence, because every sound starts with silence. The air pressure around the thing making the sound is at equilibrium with the air pressure around your eardrum or your microphone. The positive phase of the wave builds up to a moment of maximum positive pressure at the peak, and then the pressure abates down to equilibrium again, and then it dips further down into negative territory where it's pulling air away from you or your microphone, and then the pressure goes back up to equilibrium again, and then it repeats 20,000 times a second in the case of the highest sounds anybody can actually hear. If you're taking a 40,000 samples per second, it's possible that they could each fall on that moment of equilibrium that occurs twice a cycle in that 20,000 hertz sound, in which case the data you recorded about that sound would just be a succession of zeros. Silence. Now, that's a highly idealized scenario that probably never really happens in practice, but in practice, you would lose some high-frequency information in the sound that you're trying to record. So, the Nyquist-Shannon theorem tells us, among other things, that we have to sample sounds or any other kind of wave, at a little more than twice the rate of the fastest wave we're trying to record. So I'm recording myself right now at 44,100 samples per second, the standard for CD quality sound, which is a hilariously anachronistic term at this point. And honestly, 44,100 is overkill. That's actually way more samples than I really need, because honestly, almost no humans can actually hear frequencies as high as 20,000 hertz. That is the way outer limit of anything any human could hear. Really, only children can hear that. Everybody loses upper frequency sensitivity with age, for lots of different reasons, but fun fact for the Ragusea pod, it can be diet-related. Hearing loss is part of the metabolic syndrome because high blood pressure and diabetes can damage the tiny blood vessels and nerves and such in your inner ear. And you lose your upper frequency sensitivity faster than you normally would. You're still able to hear. Most old people are able to hear because most of the information we actually need from sound is in the bottom half of the audible spectrum. Like, here, I'm going to resample this audio of me talking to remove every frequency in my voice above 10,000 hertz. And here we go. This should be a noticeable difference for most of you, but not a huge difference, right? This is with the entire upper half of the theoretically audible spectrum just gone. Now I'm going to cut everything in my voice above 6,000 hertz. And this is when I will start to sound like I'm on a phone call, right? Phone systems save on data transmission costs by tossing out all of that upper frequency information that requires way more samples per second to reproduce. Lower frequencies require fewer samples per second to reproduce, and therefore they just take up way less memory. You can still hear me, because most of the information we need from sound is down in the thousands and hundreds of hertz. But what we lose is certain consonants, like S and F. When I have to spell my name for someone over the phone, I have to say R-A-G-U, S as in Sam, E-A. Because the difference between S as in Sam and F as in Frank is almost entirely a difference of really high frequencies. And so you lose those over the phone or over a radio, which is why military people say Alpha Bravo Charlie instead of ABC, because it's impossible to tell the difference between certain letters without high resolution audio with all of its upper frequency content intact. As people get older, they can usually hear pretty well except for those upper frequencies, which really affects conversation. That's why grandma can hear that you're there and she can hear that you're talking. She can hear the cars whizzing by, but she has trouble understanding what you're saying nonetheless because she can't hear high frequency consonants like H. Again, all of this is to say that if you want to record the highest sound that's even remotely perceivable by a human child, you have to record at just over 40,000 samples per second, which is a lot. That's a lot of computer memory. The scientists who put tomato plants into an acoustically isolated box with 2 microphones on it, those scientists had to record at 500,000 samples per second. 40,000 samples for the most sensitive human ears, 500,000 samples for plant ears, I guess? We'll get back to the purpose of these sounds, but what the scientists recorded was incredibly high-frequency blips, very short little sounds that just sound like a solitary click to us, and that's after I slow it down 800%. One more time, the sound of tomato pain. The authors here published their paper in an open access journal called Cell. Open access means free to everybody on the internet, yay. And they also published their supplemental material on a site called Dryad, where scholars can upload their raw data and anything else they can't fit into a journal article, like sound recordings. I downloaded the sound recordings off Dryad. The sample rate was so high that I literally could not play the sounds anywhere. No media player app on my computer can handle 500,000 samples per second. I had to slow those files down before I could even play them, let alone hear them. To make them audible, I stretched those sounds out 800%. For contrast, here's my voice slowed down 800%. Yeah, that's how much slower the click sounds compared to the sound that the tomato plant actually made. That was the slow version. They mic'd up the plants in an acoustic box. They recorded the plant under normal conditions, under various stressed conditions, and they even just recorded the empty flower pot sitting there for a control. And then by comparing all of these recordings in the computer, they could isolate specific sounds that are only present when the plant is stressed. And by using machine learning algorithms, they were able to teach the computer to tell the difference between sounds particularly associated with drought versus sounds particularly associated with the plant being cut, etc. The tomatoes that had been deprived of water for a few days made about 35 of those ultrasonic clicking sounds per hour. And the tomato plant that had been cut made about 25 of those clicks per hour. The tobacco also clicked, but a lot less often. And the control groups of normal healthy plants each made fewer than one such click per hour. Perhaps that was just random noise clouding the results. Then again, they recorded 0 clicks when they just recorded the empty flower pot. So that would indicate that even a healthy plant clicks a little, right? Can you imagine being the research assistant whose job it was to record the sound of an empty flower pot for hours? Like when that person went home and someone said, "Hey, what'd you do today?" What do you think they said? Some jobs are harder to explain than others. Some people go home at the end of the day and you know what they say? They say, "Hey, you know what I did at work? I helped bring people high quality, sustainable food today." That's what the folks at ButcherBox get to say. ButcherBox is the sponsor of this episode. Save some money right now at butcherbox.com/Ragusia. ButcherBox sends the best meat and seafood right to your door at an affordable price. 100% grass-fed beef, free-range organic chicken, pork raised crate-free and wild-caught seafood, humanely raised with no antibiotics or added hormones. You tell ButcherBox what kind of meat you're interested in getting, you sign up for a plan, and then curated, customized boxes start showing up at your house. Everything I get is vacuum-packed and frozen solid on dry ice, which means really no loss in quality. Plus, I use the dry ice to make ice cream, but that's a video for another day. ButcherBox works really hard to source product from farmers using humane, sustainable practices. And because they can buy things in bulk and such, they're able to save a lot of money with this business model and pass the savings on to you. And it's convenient. You don't have to go to the grocery store. Any meat that they send you that you can't eat right away, you just throw directly into the freezer. It's already packed up for it. So check out ButcherBox. Get free chicken thighs for a year and $20 off your first box when you sign up today. Chicken thigh is my favorite poultry cut. That's 3 pounds of bone-in chicken thighs free in every box for a year, plus $20 off your first order when you sign up at butcherbox.com/Ragusia. Claim that deal at butcherbox.com/Ragusia. Thank you, ButcherBox. Anyway, tomato plants click when they're distressed, kind of like the way an animal vocalizes when distressed. In this experiment out of Israel, the median volume of the clicks, like the loudness of the clicks, was about 60 decibels, which, speak of the devil, we talked about 2 episodes ago. 60 decibels is how loud voices tend to sound when you're sitting next to people having a normal conversation, which is why there was a podcast company called 60dB until Google bought it, which is great work if you can get it. Point is, we're talking about reasonably loud sounds here. You would hear them if they weren't so incredibly high. And the clicks don't come at regular or random intervals. The clicking is far more frequent in the morning hours and in the evening, though a little less so in the evening. Midday, the clicking slows down a lot, and at night it slows down even more. The rate of clicking was very closely correlated with the rate of transpiration. That is, when a plant releases water vapor from the stomata, the little pores on the leaf or the stem, transpiration generally slows during the heat of the day to keep the plant from drying out. The rate of clicking also closely correlated with the rate of stomatal conductance, which is the diffusion of all kinds of gases through those little pores. Stomatal conductance is also the highest in the morning and secondarily in the evening. Do you think you know what specifically is making the sound yet? The sounds tend to be slightly lower in frequency when coming from a plant with a bigger stem and or wider xylem in the stem. Think about it. The clicking increases as the plant loses more water to a point. The clicking starts faster and ends faster from a plant that has been cut as opposed to a plant that's been water-starved, perhaps because the cut is a sudden, acute injury that results in the rapid loss of various liquids and gases inside the plant. The authors here suspect that the sound is caused by cavitation within the plant. As the plant is stressed, it loses some of its precious bodily fluids, and the result is little empty spots inside the plant, cavities. Some people think that knuckle clicking, I should have warned you before I did that, some people think knuckle clicking is caused by cavitation inside the joints. Right? The authors here suspect that the sound from a plant is caused by cavitation within the plant. As the plant is stressed, it loses some of its precious bodily fluids, and the result is little empty spots. No one knows what the clicking is yet, but it seems most likely to be the movement of carbon dioxide or water vapor or whatever inside the plant, or it could be the sound of those gases leaving the plant. The authors repeated their experiment inside a greenhouse for a more realistic setting than, inside an acoustical box. Problem is, greenhouses have lots of other noise, so they had to train a computer neural network, a kind of artificial intelligence, they had to train it to filter out all of the sound that isn't clicking. And their computers were able to correctly identify the sound of a drought-stressed tomato plant versus an injury-stressed tomato plant versus a perfectly happy tomato plant, etc. The computers were able to guess correctly on that stuff like 80% of the time, just going by the sounds, that's pretty darn good. That's an indication that the scientists got everything right. Plants seem to have particular sounds they make depending on whether they've been hurt or infected, or dried out. To a point, right? The clicks fade away after about a week, and the plant starts to get really desiccated. The plant clicks a lot around 5 days without water, and then it slows and then stops after that. But why, right? Well, one thing this paper indicated pretty clearly is that the sounds could, theoretically, be heard or otherwise perceived by animals or other plants. Because previous studies had involved putting contact microphones directly onto the plant, whereas these researchers just pointed normal microphones at the plant. And if a sound can reach a microphone, then it can reach something else nearby. Few things in nature don't confer some evolutionary advantage, right? That's why those mutations stuck. So one presumes that the sound probably has a purpose. It does something useful. The sound may be a way of raising the alarm to neighbor plants. Because plants definitely do engage in signaling, you could call it, instead of communication, if communication sounds too intentional. Obviously, plants signal animals all the time, right? Plants make delicious smelling and tasting and looking fruits for us to notice and then come and eat, and thus disperse the seeds contained therein. Or some plants, like onions, make noxious gases when damaged to scare off herbivores, like riot police do. Those you probably knew about, but here's one example of plants signaling animals that you might not have heard of. This was documented at the University of Georgia in the late 1990s. A UGA entomologist and some U.S. Department of Agriculture researchers looked at these particular volatile organic compounds emitted by corn and cotton and tobacco plants. 3 crops that are native to the Americas, and I wonder if that has anything to do with it. Yes, cotton is indigenous to the Americas, by the way. It just happens to be indigenous to other continents as well. Anyway, these scientists found that the oral secretions, the saliva of certain herbivore insects, prompts the corn or the cotton or the tobacco plant to synthesize and to release volatile organic compounds like terpenoids. Terpenes and terpenoids you've probably heard of. They comprise a lot of the flavor molecules that we know and love from strong-tasting plants. Volatile organic compounds are, volatile, and thus they are easy to smell, and smell is more than half of flavor. Anyway, when certain pests, like the corn earworm, start chomping on the corn plant, damaging it, the plant releases volatile organic compounds that don't seem to repel the earworm. Instead, the smell attracts parasitic wasps that fly over to the corn plant and they lay their eggs inside the earworm's eggs, or more accurately, the eggs of the moth that the earworm metamorphized into. The wasp lays its eggs in the pest's eggs. The little baby wasps consume all the nutrients intended for the baby earworms, and the baby earworms die. The corn is sending a signal to one animal to come and kill another animal that the corn doesn't like. Do you realize what this means? This means that plants take out hits on animals. You could be next. Oh, those are some nice looking eggs you got there. It'd be a real shame if something happened to them. And this is where, if the Adam Ragusea show was scripted and animated and had big Family Guy energy, we would abruptly cut away to a little cartoon skit where Tony Soprano is an ear of corn and he's ordering some guy to whack another guy. And if the cutaway was literally 2 or 3 seconds long, it'd work. But if it was way longer, the script would need like a full-fledged joke in addition to the funny premise. If you're going to go longer than like 4 seconds, a funny premise isn't enough. You need actual jokes on top of the premise. That's something that I've found myself noticing lately as I've been paying more attention to comedy as a genre. I don't know much about it, but I feel like a lot of my work is starting to verge into comedy writing here and there these days. So I've been trying to pay more attention to the genre, and there's like whole comedy movies that have a funny premise and yet no actual jokes because the writers thought the premise was enough. They thought you'd laugh just seeing the premise unfold because the events are inherently funny, but they're not unless you write actual jokes. It's like the distinction between strategic versus tactical in military planning, right? The premise is the strategy. The jokes are the tactics. You need both strategy and tactics to win. I'm not saying I have both or that it's easy to get both. Comedy is really hard. That's why so much of it is bad. Anyway, plants send signals. They send signals to animals, but they also send signals to each other, to other plants. Other plants have mechanisms for detecting the volatile organic compounds emitted by their neighbor plants, which is to say nothing of the signaling that happens underground through shared or entangled root systems, or across shared fungal networks underground linking plants together. The mycelial network! We know from work also done in Israel about 10 years ago on pea plants that garden peas signal each other through their roots. Scientists let some pea plants grow in a shared container, spread out in like a row. They sprayed a chemical onto the pea plant at the very end of the row to dry it out, to induce osmotic stress, and within 15 minutes, the neighborhood pea plants, which had not been sprayed, they closed their stomata, their little pores, by almost 40%. The healthy pea plants sensed that their neighbor was experiencing drought conditions, so they contracted their pores to reduce evaporation in anticipation of the drought headed their way too. We don't know exactly what the signal is, but they think it's chemicals that the stressed plant releases into its root system, and those stress chemicals eventually reach the neighboring plants via their intertwined root systems. Why does the first pea plant bother warning the others? Like, what does he care? And of course, we know that the pea plant is a pea brain. It doesn't have a care in the world, nor is it a he. What we're asking is, why would a plant evolve to emit signals that only benefit neighboring plants, not the plant itself? The pea plant drying out on the edge of the row doesn't seem to have anything to gain by warning the others. Its survival is not enhanced by the act of warning the others. The survival of the other plants is enhanced, but not the poor dry guy at the end of the row who warned everybody else to close their stomata. Well, there's some research indicating that plants can effectively share water with their neighbors, and so maybe the dry plant's survivability is enhanced by warning the other plants to retain their water, but let's put that possibility aside for a moment. There's also all kinds of examples of genetic traits that spread around within a community because they enhance the survivability of the whole community, not necessarily the individual. My favorite example of this is a hypothesis about the genetic causes of male homosexuality. Bet you didn't think you were going to hear about that in a tomato podcast. But this is the kind of interdisciplinary, intertextual content that you expect, and it is made possible by Trade Coffee, sponsor of this episode. Hey, if you've been getting your morning coffee from the same old store or the same old bag from the supermarket, it's time to explore whether there might be something better for you out there. Trade Coffee is a coffee subscription service that goes out there and discovers new coffees that you might like. Then they send different freshly roasted bags to your door. You get to try new things, curated for your tastes, and the coffee will probably be a lot fresher than anything you get at the grocery. Because Trade isn't like sitting on a warehouse full of surplus coffee. The coffee doesn't actually come from Trade. It comes from a local independent roaster out there. Trade samples coffee from all the best roasters in the United States. They pick the best of the best. They sort it into categories based on the flavor, the level of the roast, whether it's whole bean or pre-ground, etc. And then Trade has the roaster ship you just the right bag at just the right time. Your preferred coffee on your preferred schedule. Upgrade your morning routine with better coffee right now. Trade is offering my podcast listeners at the moment a free bag of coffee with any subscription at drinktrade.com/AdamShow. That's drinktrade.com/AdamShow for a free bag of coffee with any subscription purchase. drinktrade.com/AdamShow. Thank you, Trade Coffee. Anyway, we're exploring the possibility that tomatoes might have evolved to scream, not because screaming helps them to survive stressful conditions, but rather it might help the neighboring tomato plants survive stressful conditions by preparing for them. My favorite example of a potentially similar dynamic from the animal kingdom is homosexuality. And this particular hypothesis applies specifically to male homosexuality. Male and female homosexuality may be genetically distinct phenomena. You would think, why would people evolve a gene that made the guys want to have sex with the guys instead of the girls? Such a community would probably breed less, and they would therefore be unlikely to pass that gene on that made some of the guys want to have sex with the other guys, right? Well, there's definitely a gene or a set of genes for androphilia, which is sexual attraction to men. There's definitely genes for gynophilia as well, love of women, and lesbians may carry that one, but probably most women have the androphilia gene. That's why most of them want to have sex with men sometimes, despite all of our many drawbacks. I mean, the list of cons is way longer than the list of pros when it comes to male partners. So there definitely is an androphilia gene. And here's one way it might have crept into some of the males in an ancient community. Maybe the whole community just had a lot of androphilia genes swimming around their gene pool, an intense genetic predisposition to go boy crazy. And while such a community might lose a little reproductive potential when some of its dudes just have sex with other dudes, the net reproductive potential of the whole community might be higher because the women are so powerfully attracted to the remaining men who are into ladies. Thus, a community-wide genetic propensity toward androphilia might result in more children being born from that community, even if it makes some of the male members of that community effectively infertile. That's just a possibility that scientists talk about. I don't think it's proven yet, but related, there is the gay uncle hypothesis, which I didn't make up. It's actually called that. The gay uncle hypothesis wonders if maybe having a few childless homosexuals in a community might have enhanced the survivability of the next generation by freeing up a few sets of adult hands to help protect and nurture the next generation. The gay uncle or the gay auntie is available to help out the other adults who are more likely to have kids, and thus the kids grow up stronger and more numerous, and they pass their genes for homosexuality along to the next generation. That's my favorite example of a way in which a biological trait might enhance community survival and reproduction without enhancing individual survival and reproduction. But there are much more mundane examples. Part of the reason most of our favorite meat animals are so easy to catch is that they, or their wild ancestors, practice some degree of predator satiation. The sheep cannot outrun the wolf, but it can outbreed the wolf. Sheep breed prolifically, and they stay together in giant herds called flocks or folds. And when the wolves come, they're going to get some sheep, but they're not going to get the whole flock. And perhaps the wolves actually contribute to the sheep getting better and stronger over time by eating the weak sheep that effectively sacrifice themselves for the whole community. Sheep don't really bother evolving to evade or fight the wolf. They simply feed the wolves a little of themselves so that the wolves eventually get full and go away. Predator satiation. Why did I evolve to scream when I'm being eaten by a wolf? I mean, one presumes I would scream, having never been in that situation before, but knowing how I generally handle things, I reckon that upon being slowly ingested by a hungry wolf, I would scream. I would scream for help, but even if I knew that no one was near enough to save me in time, I would still scream. I'm probably evolved to scream to warn the other proto-humans in my community that danger is nearby. So, is that why the tomato screams when it is dry or cut? And by scream, I mean, of course, emit 30 ultra-high frequency clicks per hour in the morning? Is the tomato evolved to warn the neighboring tomato that it's getting a little dry and hot over here, so maybe close up your pores to retain moisture? Or Is the tomato saying, hey, it's getting really windy here and my branches are breaking, so maybe release like a hormone that'll relax your branches so that they bend in the wind or something like that? Maybe they're warning their neighbors. Or maybe that's just what it sounds like when a tomato plant is without water for 5 days. Maybe a drying plant clicks for the same reason that a totally dried and dead plant rattles. That's just what happens. Maybe as the plant is in those early stages of drying, you get little empty spots vacated by water inside the plant, cavitation, and that simply happens to make a sound. Not every sound is a signal. Maybe this is just incidental noise. Maybe. Then again, the clicking was most frantic in the morning before the heat of the day. So, if that's just the sound of a plant drying, why wouldn't it peak in the middle of the day instead of in the morning? The authors of the tomato study don't claim to know. All they proved is that the clicks could function as a signal if anyone wanted to receive them as such. They proved that there is a particular sonic signature for a tomato plant in drought stress, and there's a different sonic signature for a tomato plant undergoing physical stresses like being cut. If anyone or anything wanted to know if a tomato plant is really thirsty, well, you could conceivably just listen for it. Because the other thing these researchers proved is that the sound travels, even across a noisy greenhouse. These clicks had previously been documented using contact microphones, vibration detectors that you physically stick onto the vibrating object, in this case the plant stem. They already documented these clicks with contact microphones, but this latest study used microphones across the room, 3 to 5 meters away. The sounds travel, thus they could be read as a signal by anyone who wanted to read them as such. Do the neighboring plants hear that one of their buddies is thirsty? Nobody knows. Yet, but it's not inconceivable. Plants respond to wind all the time, right? They might fold their leaves up to keep them from blowing away, and wind is a subsonic sound. Sounds are just disturbances in air pressure in waves that propagate between 20 and 20,000 cycles per second, which is really fast. Wind is a much slower disturbance of the air, so we can't hear it. We can hear the sound of wind breaking against objects around us, but in that instance, we're hearing the objects vibrate. We're not hearing the wind itself. The frequency of the waves in which big wind gusts travel is a matter of seconds. That's slow. Way too slow, too low of a frequency for us to hear. We can only hear frequencies that are tiny fractions of a second. The lowest sound anyone conceivably can hear is 20 wave cycles per second, while a gentle wind might be 1 wave cycle per every 5 seconds. We can't hear wind. And it's a good thing, too, because if we could hear wind, it would hurt because it would be so loud. Sound frequencies in our audible range are usually much lower energy, less intense disturbances of air pressure. But both wind and audible sound are just disturbances of air pressure, and we know that plants are evolved to respond to wind in all kinds of ways. Might plants also respond to much less powerful, much higher frequency disturbances of air pressure, aka sound? Well, at Tel Aviv University, they proved a few years ago that a beautiful flower, the evening primrose, is able to detect the very subtle, very high-frequency air vibrations made by pollinator bees flying by. The flower petals themselves function like your eardrum, or the diaphragm in this microphone that I'm talking through. The petals move slightly in response to the very, very subtle, high-frequency air disturbances that we call sound. Imagine a pebble hitting the water versus a boulder hitting the water. The few big waves made by the boulder are analogous to wind, and the many teeny tiny waves made by the pebble are sound. right? We evolved hearing to detect the small things happening in our atmosphere, whereas we use our sense of touch to detect much bigger things happening in our atmosphere, like a wind gust. We feel the wind, we hear the sound. Anyway, the petals of the evening primrose move in response to the sound of bees buzzing by. And what they documented in Israel is that movement of the flower petals stimulates the flower's secretion of nectar to attract those pollinators. Other flowers are chumps. They waste precious energy pumping out a steady stream of nectar all day long, whether there's pollinators around or not to help them reproduce. The evening primrose only gives out the sweet stuff when it hears a desirable pollinator around. The flower might actually distinguish between the sounds of different insects, and therefore maybe the evening primrose is evolved to only put out nectar when a particularly effective kind of pollinating insect comes around. So yeah, it is possible that tomato plants could use some of their parts as sound sensory organs to hear their neighbor's distress. The leaves of tomato plants seem awfully thick and heavy and rigid to me compared to, the delicate gossamer of an evening primrose petal. You need a very light, delicate piece of material to serve as the diaphragm in your sound sensing organ or sound sensing device like a microphone, because you need something that will move in response to incredibly tiny disturbances of air pressure. Maybe it's not the leaves of the tomato plant that hear the sounds, but maybe it's its own flower petals. Maybe it's the trichomes on the leaves, the superfine little hair structures. Tomato leaves tend to be a little fuzzy because they have lots of trichomes. Maybe the trichomes are sensitive to sound in the same way that the tiny hair cells inside our ears help us to hear. I'm just spitballing, but there's another possibility. Maybe someone else is listening to the tomato scream. Not a plant, but an animal. Like an insect. Because insects hear ultrasonic frequencies. We know this. The scientists in Tel Aviv observed that the high-frequency clicks from their stressed tomatoes were squarely within the perceivable frequency range of insect hearing. Insects like moths, and also small mammals like mice. They would absolutely be able to hear the sound of a nearby tomato plant getting a little too dry. Why might they care to hear that? No idea. Maybe, just maybe, it's easier for the caterpillars of a certain moth to eat the leaves of a dying tomato plant. So the moth flies around listening for the sound of a tomato plant that's just starting to get distressed. Remember, the clicking peaks after 5 days without water, which is the early stages of trouble for the plant. The moth listens for a tomato plant that is just starting to die, so it lays its eggs on that plant instead of on the other plants, so that by the time the eggs hatch and the caterpillars are hungry, the plant will be nice and tenderly, recently dead for the optimal chomping of those caterpillars. I literally just made that up. That is wild speculation, but something like that could happen, right? Why would it be to the tomato's advantage to evolve to make a sound that would attract a predator to it? Well, maybe it didn't evolve that. Maybe that's just the sound that is incidentally made by a drying tomato plant. I didn't evolve my voice to attract predators either, and yet it could conceivably have that effect nonetheless. Right? Or maybe the tomato did evolve the clicks as a signal to attract predaceous moths, because that way, all the moths lay their eggs on that one plant that's already dying. And thus the healthier tomato plants in that little gene pool have a better chance at surviving the drought without caterpillar infestation. I want to reiterate, I made up that whole thing about predaceous moths. I have no idea if they exist, but things like that do generally exist. Of course, another sad possibility we must consider is that up until now, no one and no thing has bothered to listen to the tomato's desperate cries. In the garden, no one can hear you scream, little tomato. That's just another possibility among many. But I guess we can hear the tomatoes scream now. We know that we are listening. And the authors of this new paper speculate that this sound could be the basis of new precision irrigation technology. Super high efficiency automated irrigation that only gives the plants the water when they really need it. Such systems generally rely on instruments that measure the moisture content of the soil, but the sound of thirst might be a better, more direct way of assessing whether the plants really need water. Such technology could help one make the desert bloom, so it's not surprising this research is coming out of Israel. But of course, I don't know if this would be a better way of managing irrigation systems. All I know is that I really needed to talk about screaming tomatoes for a full episode, and I thank you for indulging me in that. It's a topic that sits at the conversion of my most passionate interests: music, garden-grown tomatoes, and popular science. Of course I was going to do a full episode on this. And I also have to thank the young person who sent me this latest study out of Israel, Nimrod Schreiber. Nimrod is there in Israel and has actually been working on this sound of plants research at the high school level, which is pretty darn impressive. I saw the paper that Nimrod did for high school. It was in Hebrew, but it looked impressive. Anyway, thanks for the tip, Nimrod. I think I want to do some systematic testing of that whole cook your mushrooms in water, not oil thing. The internet is just wild about that technique. Everybody wants to tell me about it, and I've done it before, and I have been unhappy with the results, but it could depend on the context. I think I'm going to do some tests on that for the next YouTube video. The next podcast will be a very special episode involving some very special young food scientists of my acquaintance. Make good choices. Talk to you next time. Pew.